Here's a reality that will break your brain. When you play Counter-Strike 2, League of Legends, and Street Fighter 6 back to back, you're experiencing three completely different realities. In CS2, you exist in the present while enemies are 100 milliseconds in the past. In League of Legends, the server is God and your movement clicks are prayers waiting for his approval. And in Street Fighter 6, both you and your opponent are time-traveling wizards who are constantly rewinding into the past and replaying reality when predictions fail. These are the same problem caused by network latency destroying responsiveness. But even with three radically different solutions, why can't they just pick the best one? Well, that's what we're going to find out. Let's rewind to 1996. The good old days when your mom yelling, "Get off the internet, I need to use the phone," was a legitimate disconnect message. Back then, players connecting to Quake over dial-up internet faced a massive problem. Every action had a third of a second delay, which made competitive play essentially impossible. The original Quake treated players' computers like dumb terminals, where every keystroke had to make a round trip to the server before anything happened on screen. On dial-up internet, this was completely unplayable. Duke Nukem 3D actually implemented client-side prediction first in January 1996, but Quake World refined and popularized the technique. So in December 1996, John Carmack released Quake World with a revolutionary solution that became known as client-side prediction. The core idea is simple but genius. The moment you press a key, the game immediately predicts what should happen and shows it to you. Meanwhile, it sends your input to the server. The server validates it and sends back the authoritative truth. When that arrives, your game compares what it predicted versus what actually happened and makes corrections if needed. Now, why does the server need to validate everything? See, there are two reasons. First, there needs to be a single source of truth. If two players shoot each other at the same time, both their clients think they won. The server is the referee that decides what actually happened. Second, there's the cheating problem. If the client had final say, someone could easily modify their game to move at super speed or shoot through walls. The server validates that your actions are legal according to the game's rules. This turned that 300 millisecond nightmare into something that felt instant. And this technique became the foundation that every modern multiplayer game builds on. Fast forward to today and look at Counter-Strike 2. When you move in CS2, it feels immediate with zero delay. You tap A to strafe left, and you're moving left right now. That's client-side prediction doing exactly what Quake World pioneered. Your computer predicts your movement instantly using the same physics code that runs on the server. Then it sends your input to the server, which validates it. And when the server's version of reality comes back, your client reconciles any differences and smoothing out the corrections so you don't even notice them. But CS2 takes this further with something called favor the shooter. See, when you shoot at an enemy, you're not shooting at where they are right now. You're shooting at where they were 100 milliseconds ago, because that's what you see on your screen due to network latency. So when you fire, the game tells the server, "I shot at this exact moment." And the server literally rewinds time. It rolls back all the player positions to where they were at that exact moment in the past, accounting for your latency, and does the hit detection there. This is called lag compensation, and it means you can hit enemies right where you see them, which feels fair and responsive. But there's a trade-off. The victim occasionally gets shot behind cover. From their perspective, they ran behind a wall, but then they die. That's because from the shooter's perspective, they fired before you got to cover. The server agreed with the shooter, and that is the price we pay for responsive gunplay. Scale trade-offs. Why Apex's 20 Hz isn't worse. Now here's where things get spicy. In 2019, Apex Legends launched with 20 Hz servers, and Reddit absolutely lost its mind. Everyone assumed that lower tick rate meant worse netcode. But here's the thing, Apex uses the exact same client-side prediction technique as Counter-Strike 2. The same instant local feedback, the same server reconciliation. The only difference is the tick rate, how often the server updates the game state. Apex runs at 20 Hz, and when Respawn's lead engineer Sammy Duke explained the math, it was actually kind of brilliant. At 50 milliseconds ping, 20 Hz creates about 75 milliseconds of total delay. That's roughly 5 frames at 60 frames per second. Bumping to 60 Hz reduces that to about 42 milliseconds, roughly 3 frames. A 2-frame improvement, but the server costs triple. 3 times the expense for an improvement most players can't even perceive. Now here's the deeper reason. Apex's architecture has 10 players in relatively small maps, but Apex has 60 players with abilities, passives, ultimates, care packages, map events. seconds, and Apex sends the complete world state every single tick. That's a massive amount of data. At 20 Hz, Apex uses about 60 kilobytes per second of bandwidth, and at 60 Hz, that balloons to 180 kilobytes per second. That's higher than you can reliably buffer in real-time gaming, especially for console and mobile players. Packet loss and jitter become severe problems. You'd create a worse experience trying to force higher tick rates. So Respawn made a choice. Accept 20 Hz with reliable delivery instead of 60 Hz with constant packet loss. Same technique, same prediction, but different scale requirements and optimization choices. But here's the lesson. Tick rate is just one piece of a much bigger puzzle. Now let's talk about the rebellion. League of Legends runs at 30 Hz, and it has a setting called Use Movement Prediction. But here's the kicker, it's disabled by default. Riot Games, the developers, explicitly describe it as a lag compensation mechanism, not a core feature, and they recommend most players keep it turned off. But why would a competitive game deliberately reject the standard solution? That's because MOBAs aren't shooters. In League, you don't control your character with WASD keys. You click where you want to go, and your champion calculates a path and walks there. That pathfinding is insanely complex. The client would need to perfectly replicate the server's pathfinding algorithm, accounting for unit collision, terrain, other players, minions, everything. And then there are the abilities. Hundreds of unique champion abilities with frame-perfect timing windows and complex interactions. If your client predicted an ability and the server disagreed, you'd get jarring corrections constantly. But most importantly, competitive integrity. Riot spent nearly a full year making their servers fully deterministic, meaning the exact same inputs always produce the exact same outputs. This lets them record entire professional matches as just a list of inputs and timestamps. They can replay any match perfectly. They can rewind and fast forward for bug investigation. They can verify tournament integrity. This determinism, this perfect, predictable server authority is more valuable to League than instant responsiveness. So they chose differently. Slightly less responsive feel, but perfect competitive determinism. Server is God. Your clicks are prayers. And that's fine, because tactical gameplay can tolerate 30 to 100 milliseconds of delay in ways that Twitch shooters cannot. And now we arrive at the time wizards, Street Fighter 6. This game uses something called Rollback netcode, custom built by Capcom but using the same technique as GGPO, which stands for Good Game Peace Out. And it is completely different from everything we've talked about so far. In Counter-Strike, you predict yourself and the server tells you the truth about everyone else. In Street Fighter, both players predict each other simultaneously. Here's how it works. Your game assumes your opponent will repeat their last input. So if they were crouching last frame, it assumes they are still crouching this frame. It immediately simulates the game with that assumption. You see the result instantly, zero delay. Then, 100 milliseconds later, your opponent's actual input arrives over the network. And if it was different from what you predicted, if they jumped instead of crouching, the game rewinds. It literally rolls back to the moment that input should have happened, replays those past frames with the correct input, and fast forwards back to the present, all within a single frame. 16.67 milliseconds. That's why fighting games with good rollback need incredibly efficient netcode. They have to rewind several frames, re-simulate all of them with corrected inputs within a single frame of game time, and do this for every incorrect prediction. So why go through all this insane effort? Because fighting games need frame-perfect precision. One frame is 16.67 milliseconds. Combos succeed or fail based on single frame timing, and fighting games are peer-to-peer. There's no central server. If you used traditional client-server architecture, one player would be the host with instant response, and the other would have delayed response. That's fundamentally unfair. Rollback netcode creates symmetric responsiveness. Both players feel instant. Both players predict each other. Both players experience the same corrections. The proof that this works? When Guilty Gear XX Accent Core plus R retrofitted rollback netcode in 2020, concurrent player counts surged from 40 to 50 players to over 2,300 overnight. The exact same game. The only difference was the netcode. And suddenly, a decade-old fighting game had a thriving online community again. That's how much netcode matters. So what's the lesson here? Why can't developers just pick the best netcode and use it everywhere? Because there is no best netcode. There's only the right architecture for your specific game. FPS games like Counter-Strike, Apex, and Valorant use traditional prediction because movement is simple math that can be re-simulated cheaply. MOBAs like League and Dota prioritize server authority because tactical gameplay tolerates delays and determinism matters more than instant feedback. Fighting games like Street Fighter and Guilty Gear use rollback because it's the only solution for peer-to-peer symmetry with frame-perfect timing requirements. The reality is that game design dictates the solution. A technique that works brilliantly for one genre can be completely wrong for another. Quake World invented client-side prediction to solve the dial-up nightmare. But in the nearly 30 years since, that elegant idea has splintered into dozens of variations, each one carefully tailored to the specific needs of different games. So the next time someone complains about tick rates or netcode, remember this. They're not just asking for better technology, they're asking for a fundamentally different set of trade-offs. And in game development, every trade-off is a choice about what kind of experience you want to create. This was it for today. See you in the next one.